Greetings, machine component designers, summer 2020. I'm looking at the wrong thing there. I want to go like that so you can see me. It's another gray morning here on Bailey Island, Maine. Still a pretty good place to be during a pandemic. So today we're going to talk about residual stresses. But before we talk about residual stresses, we need to talk about like where do the stresses come from and how are stresses distributed. So we need something heavy that we can pick up. We need to load something. A sailboat. That's a nice heavy object. So let's pick up that sailboat. We're gonna pick it up. We got to keep things simple. How about in pure tension? There must be something we could use to pick that thing up in pure tension. Look at this. Look at this. Perfect piece of aluminum. 10 millimeters in diameter. Well, let's cut these parts off here. So, 200 millimeters long. So here we go. So we're going to go over here. The crane, whatever, we'll figure that out. We're going to hook the crane up to here and hook this up to the lifting bridle on the sailboat. And we're just going to lift this whole thing up. All right, we're going to lift up that sailboat. Well, actually, that's a 1972 Balboa 20. I prefer to call it a sailing yacht. So we're going to pick up our sailing yacht using this piece of 6061 T6 aluminum. Now, you may say, Dressler, it's a landscaping spike that you found laying in the yard. It's made out of steel. Yeah, it is, right? But let's, for the sake of academics, piece of aluminum here, all right? So we're going to pick this thing up just in pure tension. So what's that going to look like? Okay, so, lifting a sailboat. Let's actually call that sailing yacht. Okay, so we've got our 1972 Balboa 20. And I'm going to say that weighs about 658 kilograms. 658 kilograms, which works out to be 6,400 newtons. So 6,453 newtons, right? And I'm going to lift it with aluminum. And so the dimensions are L equals 200 millimeters long, and the diameter equals, what does the diameter equal? 10 millimeters. That's what we estimated it to be. And that gives me an area of 78 millimeters squared. Right? And let's remember that I'm doing this in newtons and millimeters squared, right? Because 1 newton per millimeter squared equals 1 megapascal. Yeah. And let's see, I'm going to put down my piece of aluminum there. And yeah, that works out well because the yield stress, so let's go back to red here, S sub Y for this particular alloy of aluminum is 270 megapascals. Okay, so let's see what happens, right? I know that the stress, so the tensile stress, sigma equals, let's see, load over area, which equals 6,453 newtons per 78 millimeters squared. And that works out to be a nice, easy 82 megapascals. Right? So that's a pretty important intermediate step, so I'm going to put a dotted box around that so people can follow it. 82 megapascals. And it looks as though my, that's 82 megapascals, that's 270 megapascals, so that, I'm good. I can certainly lift up my sailboat with this thing. In fact, the factor of safety for this guy, let's see, N for the boat equals, let's see, it's strength over stress, right? Strength over stress. So this is how strong it is, 270 megapascals, divided by what's my total stress on this thing is 82 megapascals. So that means my safety factor here is 3.3, right? That's pretty good, right? I've got a nice safety factor. That means my piece of aluminum with which I'm lifting this thing is 3.3 times as strong as it needs to be. All right. But let's take just one closer look here. And how does this actually happen? I don't consider this piece of aluminum rigid. I know that this thing flexes, right? In fact, when I pull on it like this, I pull it up here and pulling down here. I don't think of it as a boring, rigid piece of aluminum. I think of this as a spring. And that spring is going to stretch. So how much is it going to stretch? Let's take a look at that. So how much will it stretch? Whoop, get back there, close that. How much will it stretch? Okay, well, I know that the stress equals Young's modulus times the strain, right? That's not a very good strain. Let's make that better. That's important. Times the strain. Or in other words, or rearrange, strain equals, let's see, stress over the Young's modulus equals 82 megapascals divided by the Young's modulus for this is 70 gigapascals, right? But to keep my units correct, I'm going to write this as 70,000 megapascals. So that's going to work out to be a strain of 0.0012. Right, now that's dimensionless. So we might call that 1.2 millistrain. Right, because strains are typically very, very low, so we refer to them in millistrain or microstrain. But I'm not interested in strain. I want to know how much it stretches. So the stretch delta equals the strain times my original length, right, which is 0.0012. That's dimensionless, times my original 200 millimeters. Right, so that equals, I hope you can still see this in the recording, 0.23 millimeters. So what does that mean? That means that, right, when I lift that sailing yacht, 650 some kilograms with this piece of aluminum, this thing will actually stretch 0.2 millimeters. Right, now you can see a millimeter. And you can probably see a fifth of a millimeter, right? So you think about that, lifting this boat, it's a little surprising that I can lift the entire boat just with this skinny piece of aluminum, but it will stretch significantly, right? You could see the stretch in this thing as I pick it up. Okay, well, if I were to let that go then, let's see, if I were to lift and set down, right, what would this look like? So this is strain, this is stress. This here, of course, is Young's modulus, right? What would happen, I would lift it up, it would stretch, and so this would be, let's see, the strain there we decided is 1.2 millistrain, so 0.0012, and the stress worked out to be 81, right? And then when I let it go, it would go right back down to there, okay? It would go up, come back down, and it's like nothing ever happened. So I guess that didn't turn out to be as interesting as I was hoping it would be. I wonder if we have something heavier we could lift. Something heavier. Let's take a look around here. Oh, there we go. Look at that. So that is not a sailing yacht. That is a land yacht, right? In fact, that's my dad's land yacht. So what if we tried to lift that thing up? Okay, let's take a look. Lifting a sailboat, boring. Ooh, lifting a motorhome. Likewise, I'm going to cancel that out here. Let's call this a land yacht. Right, that is a 2002 Itasca Sunova. Believe it or not, my dad's had it for 18 years, and this is the first time he finally trusts me to use his motorhome. Now that comes in at a nice 8,164 kilograms, or 80,000 newtons. Okay, now let's lift that with the same piece of aluminum. All right, so the story is more or less the same. We have stress equals 80,000 newtons divided by the area, which is still 78 millimeters squared. Well, that almost cancels out really nicely. A newton per millimeter squared is a megapascal, so that works out to be 1,019 megapascals. Okay. But no, maybe not okay, because the yield strength, so SY, is only 270 megapascals. Right? That causes a problem. Yeah, that's going to be a problem. Why is that a problem? First of all, N, our safety factor, which is the strength divided by the stress, in this case equals 270 divided by 1,000. So my safety factor here is only 0.26, right? Safety factor less than 1. This means it's not going to work, okay? But the strain, if I were to try to do this, right? Strain equals, what does that equal? Strain is, I just did this. It's stress divided by Young's modulus. And so for this case, it's going to work out to be 0.0146. All right, so 14 millistrain, right? But the thing is, that's not going to happen. Why does that not happen? Because if I draw this on the stress strain diagram, what's going to happen here, right? Well, I'm just going to lift until I reach, let's see, this is sigma, this is epsilon, until I reach, sigma, epsilon, until I reach 270. Now what happens at 270? It goes from a nice rigid piece of aluminum to silly putty, right? So this is the ideal stress strain curve, right? So I can get it up to here, right? So I can probably lift, I can't lift 80,000 newtons, but I can lift probably a fourth of that, so 20,000 newtons, right? But as soon as I hit 20,000 newtons, so I've picked it up, maybe unloaded the suspension just a little bit, but it's just going to flatten out, and it stretches and stretches and stretches. So this is a stretch with no more load, right? I can lift 20,000 pounds, and after that, it just stays at 20,000. It flattens out, right? So as long as I keep lifting, right, it'll stay at 20,000. Now, if I let it go, right, it will snap back like this. So I can say I can lift up to here, really accomplish nothing to there, and then go back down to here. This will be my elastic recovery And then this part is what we call the plastic deformation. Or sometimes we call that permanent set. All right, I've actually stretched this thing. All right, so is there anything else interesting that happens when I do that, right? So I can pull. I'm not going to lift up the RV ever. It's just going to stretch and stretch and stretch. Now, of course, we know from 307 that it'll, the load will increase a little bit and then it'll eventually neck down and break. But in reality, this is what it looks like. Okay, so that didn't work. This is not enough, right? This thing is not enough. So how many do what I need? Well, I want to be safe. The safety factor on this was 0.26. Someone's knocking on a window somewhere. Should we see if we can see him? Hello, who's looking at us? And there's, if you could see through the fog, that'd be the Atlantic Ocean back there, but it's not. So we'll go back to the land yacht. All right, so safety factor is 0.26. Maybe I better multiply by 5, right? If I multiply this thing by 5, I'll be able to pick up. So I'm going to lift the motorhome land yacht with 5 of these things. Oh, lifting a motorhome, I think we're done with that. Lifting a motorhome with 5 things, all right? So I'm going to rig up some sort of a system. So I'm going to have, let's do this in, will that work? I'm going to have like a bar here, and then like maybe a lifting ring. And I'm going to have, redo. 1, 2, 3, 4, 5 of these things. And then underneath here, let's go with that one. I'm going to have my motor yacht, right? Okay, draw some wheels in there. So I'm going to lift it with 5 pieces of steel instead, right? Okay, so now, previously, so each, the nominal force, let's go back to red maybe for no better reason. So the nominal force in each one of these, instead of lifting the full 80,000, right, it's 80,000 divided by 5, which equals 16,000 newtons. Each one now has to lift 16,000 newtons. And then so the stress nominal equals, what should that equal? 16,000 divided by, so that's 1,000. No, that's the wrong one. Stress nominal is 204. megapascals, right? And so what was the yield strength again? 270. So yeah, this will work, right? The yield strength is 270. My nominal stress is only 204. So that that'll be fine. But what happens, right? Let's do this in black. Yeah, what the heck? So what if the center one, bolts, how about that? Let's call it bolts. The center bolt carried 2.5 times the nominal force, right? Or in other words, we could say there's some stress concentration. Redo. Stress concentration some KT equals 2.5, and that's going to apply to this one here. Right? I don't know why that is. Maybe because that's where that lifting eye attaches. Maybe that's just, I don't know. Due to geometry, somehow the KT equals 25 or 2.5. Right? The theoretical stress concentration factor. Okay, well, when I lift these up, they're all going to stretch by the same amount. Well, no, that's not quite right. A stress concentration factor could also be called a strain concentration. And you remember that from ME 307. Too much work for one credit. Strain concentration, right? Which means the concentrated strain would equal the concentrated stress. So 2.5 times 204 divided by the Young's modulus, E, which is 70,000. So my concentrated strain here is going to work out to be pretty high, 0.0073. Okay, so what does that mean? It's going to strain by 0.0073, but, right, my strain at yield right, if I went back to this ideal stress strain curve, where did that go? I thought I drew it somewhere. No. This spot right here is 270, and no, that strain goes first. Sorry. So I'll go back to the black one. Right, the strain when it yields is only 0.0039. Right, so we could have a yield stress and a yield strain, right? And that yield strain is 0.0039, which means that if I'm going to strain a 0.0073, a lot of that is going to be plastic. So what's that going to look like? Let's draw another ideal stress strain curve. So we'll go do it in black again, kind of arbitrary with my colors. Strain, stress. I know that it's going to go up like this and then over like this some. I'll do that in blue. So when I actually load this thing, it's going to go like this, right? Because I've got to reach this strain, which is 0.0073. Right, but I know a bunch of that is going to be plastic deformation, okay? So it's going to be carrying more than its share of the weight, but then it's also going to strain a bunch, right? So now, what if I set it down? Right. So what happens when I set it down is that these, I think I did them in blue. Yeah, okay, so these blue ones here, so here's the 5 original, let's call it, the 5 original bolts or whatever I'm using, right? And they all stretched a little bit, like that, but this middle one, due to the stress concentration, stretched a whole bunch. It stretched a lot more, all right? So when these all snap back, so some of this is, so there's a little bit some epsilon elastic, and then this is going to be plastic, right? So when I set this back down, these two are going to return to the 4 are going to return to the original shape. But this one is going to have, it's longer now than the other ones. So it gets smushed back down relative to the other ones. Like that. all right? So when this gets smushed back down, what happens to it? It goes down like this, because it goes all the way back down to its original shape, right? So I deformed elastically, right? And then I deformed plastically, but then I got compressed all the way back down to here, right? Because that one was now longer. So I know that the elastic deformation, what color am I going to do that in? I'll do it in black. Again, no reason. My elastic deformation was just up right until yield, and that was 0.0039. Right. The total strain from lifting, I discovered, was 0.0073. That means there must have been some plastic deformation, which was the difference between that, so it's 0.0034. Wow. All right, so there's a lot of plastic deformation, and when that gets compressed back down, right, so the stress resulting from that, the residual, because it's compressive, it'll be negative 240 megapascals, right, which is compression. Right. And so then I could look at that and say the force residual equals the stress residual times the area. And so that means I'm going to be left with 18,000 newtons. Right, 18,000 newtons. Let's talk about that just a sec. Okay, so here's my original thing, right? I'm going to lift it up. It stretches a little bit elastically, but then it stretches a bunch more plastically. And so when I set the RV back down on top of it, it's compressing a longer one, right? But it has to match up with the other four, right? So this one is going to get compressed down. So actually, rather than just being relaxed, it's going to actually get compressed, right? So it's going to result in a big compressive stress. However, when I take this lifting bridle or this lifting yoke, whatever they call this thing, and I set it just, back down on the ground, the net force has to be zero, right? Which means that this is going to remain in compression. Like that. That'll be in compression of 18,000 newtons. Right? And these other ones are all going to be left in tension. Too much coffee. My hands are shaky. But I always drink too much coffee. Right? And so it has to balance out. So that'll be 18,000 divided by the other four. So that's 4,700 newtons. Right? So because I deformed that one plastically, compressed it back down for these to all have the same original length, the four of them that didn't get concentrated will have 4,700 newtons of compression or tension to balance out the 18,000 newtons of compression that are due to the fact that we stretched this thing plastically. So there you go. I erred to the side of fast. You can watch it again. Certainly feel free to contact me with questions, and we'll call that good.